Hello, my name is Joseph Whitlow, and I'm a senior majoring in computer engineering.
My name is James Leho, and I am a computer engineering student.
And for our senior design project, we wanted to focus on the desalination of ocean water for drinkability and other various usages. The problem relates to the fact that as we progress in society, the need for water is going to increase, and the access to clean water is going to decrease. An example of this would be with China. They have a large population and have a very well developed agriculture. However, since they have a large population, their agriculture demand is not going to be able to keep up due to this lack of water. The largest water supply we have access to is the ocean, but it's not a reliable source since it contains a high concentration of salt, which normally would cause a person to be sick through normal means of consumption. There are existing solutions that use ocean water. So most of them tend to be a lot of resource intensive. For example, this would be India. They use a system called reverse osmosis, but it requires a lot of electrical energy, which causes a lot of power outages within that area. So we want to make access to this desalinated ocean water while it's also being inexpensive and not so energy intensive. Some existing alternatives that exist are reverse osmosis. Reverse osmosis pushes water through a semi permeable membrane to separate the water from salt. The problem is that it requires the usage of an industrial system that is too expensive to build. And like I stated with India, it requires a large amount of energy. Another alternative is distilling. Distilling evaporates water through heat and then condenses the water vapor through cooling as a way to collect clean water. The problem with this is that it also requires a lot of energy to power the heating and the cooling systems. These methods are insufficient in the fact that they require access to necessary finances and resources, which some areas just don't have access to. So this leads us to believe there is a need for a more environmentally friendly ocean water desalination method. Our proposed solution is electrodialysis. This method uses electricity to pull water through a membrane to separate water from salt. We will be using this method in a way that it pulls the chlorine and sodium ions through semi-permeable membranes, thus desalinating the water. The benefits to this method is that it does not require large financial cost, and it requires less energy than existing methods.
Before we get into the prototype, I will define some of the key terminology that is necessary to understanding our project. An ion is a charged atom molecule or radical, the migration of which affects the transport of electricity through an electrical solution. For example, if a crystal of salt is added to water, the water molecules will orient themselves around the charged atoms and nullify the attractive force between them. This is known as the solution and dissociation of salt into water. When this occurs, two electrically charged particles are formed. One, which is the cation, is the positive particle, is sodium, represented as Na positive. And the other, the cation, negative, is chloride, represented as Cl negative. In order to control the flow of the water, we will be using ion exchange membranes. First of which is cations, which only allow cations or positively charged particles to pass through them. The second type of ion exchange membrane is anion exchange membranes, which only allow negative particles or anions to pass through. For our prototype, we designed a desalination cell with 3 wells separated by 2 ion exchange membranes. On the left side is the anion transfer membrane, and on the right side is the cation transfer membrane. When an electrical current is applied to the water, these two things will happen. The cations will be attracted to the cathode on the right side, so they will migrate through the cation transfer membrane and go to the cathode. On the other hand, the anions will be attracted to the anode, and they shall migrate to the left through the anion transfer membrane to the anode. The two membranes prevent the opposite particle from moving in that direction, And what you get is two streams of highly salinated water on both the left and the right. And in the middle, we have a low concentration desalinated stream of fresh water. Our goal for the rest of April is to finish making the simulation program with Python and the formulas we've been researching. We will use the simulation program in order to validate the prototype we've been designing. Once we're able to get back to campus, or if not, possibly next month in May, we hope to finish making the prototype by collecting the materials and finish up the 3D printing. After that, we will test the prototype, and based on the results, we will start working on the final build. And after that, we will take all of our results and accumulate them graphically.
Some learning and learning we will be having in the future have been coming from the research we have done from our scholarly articles. We also had to teach ourselves some concepts from chemistry. Examples of this would have to be electrodialysis, ion behavior, and molar mass. As we continue to develop our project, I'm sure there's going to be other concepts we will be learning from chemistry as well. We hope to be able to learn so we can create an efficient and resource reduced device.
The items in our budget are the anion and cation transfer membrane, as they are necessary for any electrodialysis or electrodialysis reversal. The other items are the salinity tester for testing the validity of any prototype we build, and plexiglass and filler and primer spray paint for building the actual physical desalination cell.
That is our project up to date. Thank you for watching again. As of right now, we're continuing to research for our project, and we are also creating a simulation. Thank you, and take care.